Assalamualaikum and good day everyone. We are group 9 and today we will be presenting our topic entitled Constructing a 100 times 1 minus alpha percent confidence interval for beta. This presentation is part of Mathematical Statistic 2, Assessment 2. Throughout this presentation, we will explain the concept of confidence interval, derive the formula for constructing a confidence interval for the parameter beta using chi-square distribution, and demonstrate its application. Before we begin, let us introduce our team members. First, we have Naziha binti Sulhili. Next is Ilham Muhammad bin Samsul Kaha. Me, myself, Aina Sofia binti Abdullah. And lastly, we have Sharafana binti Suharto. Each member contributed to different parts of this project. Before discussing the derivation, let's first understand what a confidence interval is. A confidence interval is a range of value used to estimate an unknown population parameter based on sample data. Instead of providing only one estimate, it gives an interval that is likely to contain the true value of the parameter with a specified confidence level, such as 90%, 95%, or 99%. In this presentation, we focus on constructing a 100 times 1 minus alpha percent confidence interval for the parameter beta using the chi-square distribution. Understanding confidence interval is important because they allow us to measure the precision and reliability of statistical estimates.
In this project, we will be answering question 4 from past year question July 2025, focusing on question C, question 4C and 4D to construct a confidence interval for a parameter when given a function of random variable with its distribution involving that parameter. Question 4C asks us to construct a confidence interval for parameter beta if U follows a chi-square distribution with 8 degrees of freedom. There are 5 concepts or steps to derive a formula for confidence interval of parameter based on theorem. First step is to identify the function of random variable involving parameter of interest. Our parameter of interest in this question is beta, and the function of random variable involving that parameter is u, given that u equals to summation of wi, where I goes from 3 to 10 over 2 beta. This is given from question 4b. And the second step is to determine the distribution of the function of random variable, which is u follows chi-square distribution with 8 degrees of freedom. The third step is to find the critical value for both-ended side of the distribution. Since u followed chi-square distribution with 8 degrees of freedom, the left critical value for u is denoted by chi-squared 1 minus alpha over 2, 8, and the right critical value for u is denoted by chi-squared alpha over 2, 8. The blue shaded regions represent rejection regions, each with probability of alpha over 2, and the unshaded region is known as the confidence region or acceptance region, which has the probability of 1 minus alpha. The fourth step is to write the probability of function of random variable in between both critical values.
Moving on to step 5, our goal is to subject our parameter of interest, beta, directly in the middle of the inequality. The lower bound on the left, we take the sum of w sub I from I equals 3 to 10 and divide it by 2 times chi square sub alpha over 2, 8. From the upper bound on the right, we take the exact same sum and divide it by 2 times chi square sub 1 minus alpha over 2, 8. We rearrange the mat and flip our fraction to isolate beta in the center. And finally, by isolating beta from the previous page, we get our complete 100 times 1 minus alpha % confidence interval for beta. To calculate the lower bound on the left, we take the sum of W sub I from I equals 3 to 10 and divide it by 2 times chi square sub alpha over 2, 8. From the upper bound on the right, we take that exact same sum and divide it by 2 times chi square sub 1 minus alpha over 2, 8. Because we flip our fraction to isolate beta, this chi square critical value naturally swap places, leaving the larger value under our lower bound and the smaller value under our upper bound to give us our final answer.
For part D, we are required to find the 90% confidence interval for beta, given that the summation of W terms from I equal to 3 to 10 is 13. Since the confidence level is 90%, we have alpha equal to 0.1, so alpha over 2 is equal to 0.05. Using the confidence interval formula obtained in the part C, we get the interval from sum of Wi from I equal to 3 to 10 over chi square alpha over 2 with 8 degrees of freedom to the sum of Wi from I equal to 3 to 10 over chi square 1 minus alpha over 2 with 8 degrees of freedom. From the chi-square distribution table with 8 degrees of freedom, we obtain the critical values of chi-square 0.05, 8 is equal to 15.507, and the chi-square of 0.95 degrees of freedom of 8 is equal to 2.733. These critical values, together with the summation of Wi equal to 13, are then substituted into the confidence interval formula to obtain the 90% confidence interval for beta.
After we substitute all the value into the formula, we calculate the lower limit as 13 divided by 2 times 15.507 equal to 0.4192. And for the upper limit, 13 divided by 2 times 2.733 equal to 2.3783. Therefore, the 90% confidence interval for beta is from 0.4192 to 2.3783. This means that we are 90% confident that the true value of beta lies between 0.4192 and 2.3783. This interval provides a reasonable estimate of the unknown parameter based on the sample information and the chi-square distribution.
To wrap our presentation, we would like to share our lesson learned and reflection. First, by split tasks based on what everyone is good at, such as math setup, calculation, and slide design, we were able to peer review each other's work and catch silly mistake early. Second, we practice typing out big piecewise function and complex fractions so the slide look clean and uncrowded. Third, we learn how to use a helper variable to build our interval and discover that solving for a fraction reverse the inequality sign, which physically swap our upper and lower chi-square table value. Lastly, we realized that instead of just guessing a single number, creating a reliable range gives us a 90% long run success rate of catching the true population value.
As the conclusion, our group successfully applied the chi-square method to derive the formula and calculate the final 90% confidence interval, which is 0.4192 to 2.3783. This project helps us understand how confidence intervals are used to estimate population variance and how statistical concepts are applied to real-world data. We also learned the importance of accuracy teamwork and clear communication throughout the project. That is all from us. Thank you for listening.